ME204, Equation of Motion in Normal Tangential Coordinates. Let's look at some curvilinear motion examples. We can characterize the motion as we go around a traffic circle, but really what we're interested in is what is the friction force on the wheels of the car as it goes around the traffic circle, or what are the forces that a person driving in the car might feel as they go around that circle. We can characterize the motion of a swing, a person on a swing, but maybe what we really want to know is what's the tension in the chain of the swing as it goes through this motion. For a half pipe, we can characterize the motion of the skateboarder, but maybe we want to know what the forces are that the skateboarder will feel when he reaches the bottom of the half pipe. To solve these kinds of problems, we're going to look at the equation of motion for normal tangential systems. If you look at a car as it travels around a path, we can figure out what the forces are acting on that car by looking at a Cartesian coordinate system, looking at the accelerations in the x and y direction, and then calculating what the forces are in those directions as well. But it's a little bit easier to solve these problems if we look at them in a normal tangential system. Solving these problems with a normal tangential coordinate system is much the same as solving these problems in a Cartesian coordinate system. The only difference is how we're going to align our axes. We're going to choose one axis that's in the normal direction, and we'll choose one axis that's in the tangential direction. Note that these axes are always perpendicular to each other. We also know that our normal acceleration is equal to the velocity squared divided by the radius of curvature. In these types of problems, it's usually best to choose our axes along the normal tangential directions. If there's motion along a curved path, we will always have normal acceleration. So the sum of our forces in the normal direction is equal to the mass times the acceleration in the normal direction, which is equal to our mass times the velocity squared divided by the radius of curvature. The force that keeps the object following a circular path is called the centripetal force. The tangential direction may or may not have any acceleration along the path. However, we can find the forces in that direction by saying that the sum of the forces in the tangential direction are equal to the mass times the acceleration in the tangential direction. If there's no tangential acceleration, then the sum of our forces equals 0. Once the free body and kinetic diagrams are correctly drawn, the equations in each direction can be written and solved. Here's an example. Maybe we have our car that's going around that circular path. We draw in our coordinate systems for our free body and kinetic diagrams, and then we can label those with forces in the normal direction, which is our centripetal force, is equal to our masses times the acceleration in the normal direction. In the tangential direction, we draw our forces on the free body diagram and our mass times acceleration in the tangential direction on the kinetic diagram. Then we can set up the equations and solve the problem. Here's an example. We have a toy car that has a mass of 35 grams. If a track is set up that has a bump with a radius of curvature of 0.818 meters, how fast does the car need to be going to just leave the track? Well, let's start by drawing our free body diagram. Here's our car. If we neglect any air resistance or friction, then we have a weight associated with the car, and there's a normal force associated with the car as well. For our kinetic diagram, we have a mass times a normal acceleration as long as the car is traveling at a constant velocity. For the car to just leave the track, the normal force has to go to 0. So this goes away. We can calculate the weight of the vehicle as the mass times the acceleration due to gravity. So we've got 0.035 kilograms times 9.81 meters per second squared. Our mass times the normal acceleration is equal to the mass times the velocity squared over the radius of curvature. And we know that the radius of curvature is 0.818 meters. So our mass times the normal acceleration is equal to 0.035 kilograms times the velocity squared divided by 0.818 meters. So in the normal direction, the sum of the forces in the normal direction are equal to the mass times the acceleration in the normal direction. Some of our forces in the normal direction only include the weight, as seen right here. Our mass times acceleration is the mass times the normal acceleration. Notice that in this case, our masses cancel. Solving for our velocity, the velocity squared is equal to 8.02 meters squared per second squared. And taking the square root of that, our velocity is equal to 2.83 meters per second. So if we're traveling at 2.83 meters per second, the car will just leave the track. Our next topic will be the equation of motion in normal binormal coordinates.